So, once again, good afternoon, and I want to welcome you again to today's Maniac Talk. This is a special kind. In the past, we've been hosting scientists from the other sciences, but we decided that we want to go center-wide beginning this year. So, Henning is actually the first one from 500 to do a Maniac Talk. As usual for most of the Maniac Talks, I like to start with a story, a short story just to sort of warm the room a little bit. Now, this is set up in the 1950s, somewhere in the central part of Kenya. And I chose 1950s story because this is when he wrote the first book, how to use a space telescope. So I decided that would be a fitting tribute to what he's going to do today. Now, this story is about this blacksmith. Blacksmiths were very respected people in my own culture. And because, they would go out there and look for these, the soil kind of thing. And then they would melt it. It would take a lot of time to do that. And then people would use that to make steel. So they were well respected in the society. So this blacksmith is out there. And in the field, he has a pregnant woman or a wife at home. And he's very busy with this thing. Very, very busy, dedicated. And then there's this bird that comes out and starts singing a song to him. And I'll just, verbalize it in my language a little bit, but then I'll translate it directly. And then we'll say something like, so what that means is that you blacksmith who is very busy with your things, please hurry up. Go back home, your wife is about to give birth. And then the guy continued doing his thing, ignoring this bird. And the bird would come back again and sing the same song. And then he realized, I think I ought to do something here. And then finally he decides that he wants to go back home. And then when he gets there, just close to his house, he discovers there is an animal, a mythical animal, we used to call it Irimu. It used to have godlike powers. It would change into a human being. Sometimes it would have several heads, all kinds of things. But now it's behaving like a human being and it's knocking on the door of this woman and telling her, please open, I'm here to help you deliver the kid. So when the blacksmith sees this human-like animal, he immediately recognizes it, and then he's a blacksmith, he has a spear, and then he goes for the animal, he kills it. It has a happy ending, he's there on time, and the child is delivered. Now, today's speaker, obviously, has also had those kind of moments. Remember the birds speaking to the blacksmith. How can the bird communicate to a human being? These are the sixth descent. So he got a sixth descent sometime after teaching for many decades at the American University. And he found that NASA is needing some talent like mine. And he came here, he's done a lot of work, participated on so many projects, GOES, for example, the Hubble Space Telescope, the James Webb, he's also participated on that one, and many other projects while he has been here. He's going to talk about some of those things, starting his career way back when, and then take us to where we are and where we're going. Please help me welcome our speaker, Henning Leidecker.
Thank you so very much. Human beings don't really have beginnings. There's some times in my life the birth might be regarded as a start. It's certainly not a beginning. Human beings start with genes and with culture that goes back for centuries and centuries, millennia even. That's what determines them. You pick a starting point only for storytelling. But I'm going to tell you immediately what the story punchline is. I had the good fortune to find my way to Goddard Space Flight Center, and I found it to be a compelling experience. I was chasing a graduate student down to try and help him get graduated, and took a sabbatical out here to work with him on it, and learned, golly, the projects being done here are world class. They are superb. The people here include many who are absolutely superb, and likewise the teams, which are not people, they're combinations of people and a different thing altogether, and that works at Goddard in many cases also. So I decided to stay. I had just finished about 16 years at American. That was one career, and so I thought I'd try another. So that's the message, that this has been a wonderful place. Now, going back to another storyline, genes matter. Genes make me human instead of a tree or a blue-green algae. And they also have some other effects, and I'm hoping that one effect is longevity. In reviewing things that I'm not going to talk about today, but I was reviewing them for this talk, the ancestor chain, I was pleased to find out that most of my ancestors lived into their middle 80s or early 90s, and were still able to chew their own food and talk their own talk. And that gives me hope that there's a chance I'll be able to finish the lecture today. Certainly dominant in my own upbringing was being born just before the bombing of Pearl Harbor. That meant that my father was immediately transferred from where I was born, Birmingham, Alabama, up to Albertine Proving Grounds. So I spent some time in Baltimore, a few months. That's when I ate the rat poison because I had a sweet tooth, and remember having my stomach pumped on this and walking down the steps asking for the ice cream. My father would get up at 7 in the morning, and I'd see him again at 9 at night, so I didn't interact much with him. They let me stay up just long enough to say hi, and then it was off to bed. Now, what he was doing during that time, we were retransferred into District Heights, was going down to Washington, D.C. Mall and putting up to leading teams that would put a couple hundred to 2,000 phones in the temporary buildings that those of you who know Washington, D.C. from the 50s and such still will remember there. He had gone to work in Brooklyn when he was 17, soldering for AT&T. And he was meticulous and good, and so he was promoted, and they turned out that he found that he had troubleshooting skills. He could walk into these large switchboards and bang on it a few times and sniff on it and know what was broken and then make it work again. I didn't realize I'd wind up doing much the same thing, actually. So genes, I suppose, again. Reviewing the family tree, I find what the British would call below stairs people. We were active in shops. My grandfather was a baker. My waitresses, waiters, storekeepers, those sorts of folks. Forget-me-not shop, a little curio shop. So I was reflecting. There's no scholarship in the family on either side, back as far as I can find out. Was the first one to go to college for lots of folks around. And it made me reflect that going to college or scholarship is a rare way to spend time, actually, across the whole human race. There are not too many people who do it. Mostly it's earning a living in however way you can. I'm wonderfully blessed by the habit that my father had of being interested in gadgets. And he pursued that interest by bicycling and fixing his bicycles and designing new ones and bringing home the stuff from AT&T. So I grew up with really good tools and lots of wire and telephones and generators and such, and guidance in how to put them together. But the guidance was they generally only go together one way. My father was busy with his work and couldn't help that much. They had books, and that was absolutely critical. And an attitude of learning. Now, at 3, I noticed that the moon path across the sky, as viewed from my living room window, tracked the sun's path, and I measured the it worked out beautifully. So I thought I would capture the moon in particular. The sun seemed a little too hot, and I was pleased to notice that at a particular time of the evening, the moon was just grazing the roof line of the house across the street, and by gosh, the guy had a ladder. So I went up the ladder and I'm walking across the roof line of the house being disappointed that that beautiful crisp moon isn't there. It had dodged over a block away, and I thought, golly, this could go on for a long time if it's going to keep escaping like that. And then I heard my mom walking along the roof very timidly trying to bring me down again. I could see the moon at that time. Later, nearsighted, probably driven by book reading, made it impossible for me to see without very strong glasses. But at that time, I could see what I now realize was the rays on the crater Tycho. The news on the radio and our family schedule was dominated by World War II. And I had a clear impression that, gosh, we were losing it in 1943 or so. The battles were not going our way. What I didn't know was that we were building up an industrial capacity which was astonishing, and not only overwhelmed our enemies with materials, although certainly the Soviets played an important role as well, but also prepared a staff of people in the country from which the industry and leadership of this country drew for decades. We've used them all up pretty much. We're on our own in post-World War II training. It does represent a big difference. One thing I remember that was really terrifying was the images of the war that I would see at the movie theaters, or my father had a film projector and he'd hang a sheet up and we'd project the movies that he would get through the mail. And there were these horrible images in these movies. And I had no idea where they were. I didn't know if they were over the hill. And I've met other kids with the same problem. It was clear that there were terrifying things going on, but the locations were not made clear, and so I kept wondering, looking up the street, whether I'd see the tanks coming down it. It was disorienting. But escaping into the magazines my father had was a wonderful thing, and I couldn't read at 3 or 4, but I could look at the pictures and I could get the go of them, at least some of the pictures. And I found that a fascinating thing, to capture the patterns that the cutaway images made, and it set me off in one direction. For many years afterwards, I would try to capture the going of a thing by making sketches of it, cutaways or others, and had no one around to give me the examples that there are other ways to know things. When I was teaching my son Jonathan, I tried to make it clear that sometimes mathematical patterns are also available to help you understand. It took me until high school and really college to cotton onto that. It's the lack of that kind of attitude of scholarship in the family. And perhaps the internet will make it more accessible to people now, but by golly, it certainly distracted me for a long time. Knowing the go of a thing meant making a picture of it. And then, of course, there was this appalling event. Now, my father had a brother. He was on a ship scheduled to land in Japan. Each of the troops on that ship knew they'd be dead in a few hours from the behavior of the other landing parties on the fiercely contested islands in the Pacific. And the ship was torpedoed, so he never got to land. And he was one of the few who was rescued from it. And they were rounded up and put on another troop ship to go back into Japan. And then this happened. And modern scholarship indicates that the Japanese emperor was about to surrender anyway. But certainly this played a large role in it. And I was fascinated with airplanes, and we would see the B-29s and others flying over our house because we were close to Andrews. And it made the war close to me. And to see that one of them would do this was a sobering experience. For many years afterwards, I would jolt awake during a lightning storm with the blue flash and the bang, wondering what had just happened, and was it something like this? So we moved, and I got ready for grade school, and my parents prepped me for it and said, "You're going to love it. There's kids your own age. You'll learn things. You'll do things. It'll be a swell experience." And they sent me off on the bus 3 miles away to the first school. And they asked me, both grilled me when I got home and said, "How'd you like it? How was it?" And I said, "It's pretty good. I liked it. It was not so bad at all." Yeah. So I'm daydreaming the next morning, and they come in and they say, "Time to get ready for school." Again? Somehow that aspect of the preparation for it had not come through. It was rather crowded school, lots of us there, and so the teacher had discipline control issues. A lot of the kids, of course, had grown up without their fathers being present every day, and there could be discipline issues, and they were handled by practicing some of the techniques learned from the Nazis. So it had its own entertainment. It was still the case that there was a lot of airplanes in the sky, and this was great for me because I was just in love with aviation. I wish I could play for you, but you have to be there, seeing a flight of 12 B-36s go overhead at low altitude as they're getting ready to come into Andrews with the engines adjusted so they heterodyne for various reasons. It's a sight like, or a sound like none other. And my parents got me toys to play with. There was an erector set with which I built the bridges and learned how to turn a screw, which turns out to be a very useful thing to do. So how to bolt things together and make it work. They also had a book on astronomy. And I turned the pages and got some sense of the scale of the universe from it that I hadn't before, as the universe was known by the author in 1941. And this comes towards the end of the book. This is a copy of what was in the book. It's the Sombrero Galaxy, of course. And I stared at that for hours. The concept that there could be more than 1 billion stars, and they could be organized in this kind of arrangement, this kind of pattern, struck me as haunting and thrilling. And I wondered, how can this be? What are the dynamics of it, both from the mechanics of the motion and from the optics? What's going on with that core? What's going on with the donut? So books can be nice. This is a more recent photograph, and you ask the same questions, I think. This, of course, is one of the contributions of modern astronomy. We know a little better what we're looking at. We can see the intensely bright core, which actually is pin-like 14th magnitude, and now we know contains a black hole, and other events surrounding it. Gorgeous stuff. So I'm in 3rd grade. I'm looking at my Scripto notebook, and the back of the cover, this table, suddenly started flashing at me. I don't mean an epileptic fit. I mean a delight of rapture in the patterns that began to flow out of the page. I could see the rows and the columns, the diagonals in particular, all falling into order. So this is the only value the number in that place could possibly have. And it made me wonder what other relationships might be present in this table if I stared at it longer. What else could I see? And then I began to become aware of a pain in my ear. Sister Caligula had been trying to get my attention. I was distressed that I was not paying attention to her, and she was elevating me from the chair by my ear. And it took a while to get over this. It was hard to concentrate in class, keeping one eye on where she was. And later, at the movie The Blues Brothers, the remarks about time to go see the penguin had special meaning for me. The grade school was adequate. It prepared me for exams and got me into college or high school, where we had Benedictine nuns, and they are scholars. And it was a radically different experience. When I emerged from that, I was aware of a lot more, but there were still these puzzles. I was growing up with the World War II, kill the enemy, organize the entire country to kill the enemy. And I had these images of the final battles in the Pacific Ocean. One of them is a GI walking along a series of bunkers, and he's got this satchel, and he's arming a grenade and throwing it into the bunker, and arming another grenade and throwing it into the bunker. And 10 feet behind him, each of the bunkers is blowing out. And this is the way they cleaned out the island. These guys had been shooting at them. They knew from experience that if they hung a flag out, it would be chewed off and used as a weapon. So it was brutal. And that was that reality. And yet I was working with the Baltimore Catechism in Sunday schools and such, and they say, love the enemy. This is a tension. And it is a tension to me yet today. So I have a special respect for people like Gandhi and others who articulate this. I'm still bewildered. The science books I was reading did make the message, what we know is provisional. Things have changed in the past. As we learn more, we may change some things again. And then the Baltimore Catechism is making the plain statement that there's a canon which is unarguable. It is known to be true and it will never change. And this is presented a challenge for me. How can I develop a super pattern that would embrace these parts? Mom and Dad, God bless them. This still brings back wonderful memories. Got it when I was 10 and just looked at everything in the house, salt crystals, hairs, and learned how to handle these things. And that was a good thing to learn about. It was very nice to be comfortable with a microscope and very nice to be comfortable with the different range of scales of being. So not just the stuff I could pick up and touch, but stuff to magnify. Looking at the hands of a watch and watching the hands move around tick by tick was a nifty thing. So I read up on microscopy, and I learned how to use it in dark field and such. You can get a lot of a $10 Gilbert microscope. At that time it was $10. And a chemistry set, oh boy! This image is good enough if you're up close to it that you can see the potions and lotions that you could buy there. Now we can't even use them in our lab without certificates. We can just about handle water, but only when the fume hood is on. So these were different times. And we had lots of fun going down and getting sodium and throwing it into the lake, and in general, creating commotion. There was no sodium in this kit, darn it. We had to do get it in other ways. This, of course, was the Holy Grail. Everybody wanted one of these. And there were some sold, but they were rather expensive, and I wasn't able to get one. I had to wait until college before I could do this kind of stuff. I could hardly wait. I was speculating with having this Boy Scout telescope, which actually had a pretty good achromatic lens in it. But it wasn't powerful enough to see the features on the moon that I wanted, or planets. And it occurred to me that we've got this image hanging in space formed by the objective. And I could project it onto a piece of paper. It could be made to be a real image. It's called a real image. And so the obvious thing to do is to take the microscope apart and put the barrel of the microscope in and examine the image. And it worked like a champ. And I now had a 40-power telescope with pretty good resolution. I could now see the craters on the moon that I wanted and copy sketches into the notebooks and see some planetary features. It made me want, of course, more aperture, the universal the thing. And it took me until high school before I could get things together and grind a lens, grind and polish a mirror and get some more aperture. And now I have a number of telescopes in the study and no time to use them. So it's, but that was fun, and it set me up to write an article for Boy's Life. And I sent it off and naturally expected to get a response, and the response was a check for $50 and send more, which was very pleasing. And my mother had been preparing to console me when I got we have no need for your product. And so she was left speechless when the letter arrived. But another trend besides the optics was, now here my father is making me awash with wiring and stuff, and I'd done the buzzer thing. I mean, I had built a buzzer, I'd built a telegraph, I'd built a telephone, and but all around me were the radios. And the one feature that my father did drill into me, and all of the textbooks were drilling into me, is a circuit is a closed loop. You gotta have a loop for the current to circulate around. And so here we have a radio, and the apparent feature of it is an antenna. And so where's the other loop? Or rather, where's the other wire? And I figured, here I am, I'm I guess 11, and I'm obsolete and used up. The world knows about radios. I don't know about radios. What shall I do about it? Now, I mentioned that partly because there was really no one to ask. No internet. The teachers in the grade school had no comprehension of how radios work. My father didn't happen to go in that direction. So I was left with only books, and I could not find a book that would speak the language I knew how to use. So I figured the one thing I got to do is build some, and gosh, get them to work. And whatever it takes to get them to work, that may teach me what radios are about. So I took a 100-foot antenna, found a good ground, wound a tuning coil by taking a doorbell apart and using a cardboard roll, and put the slider on it from a tin can, spam can actually. And then I had headphones, but what I didn't have was a detector. So the rules are simple. You go down to the drugstore and you buy a can of sulfur. I don't know if you can still do that. and you get lead. I'm sure you had trouble getting that. And you boil them together in your mom's pot when she's not looking. And you get, you create lead sulfide, galnia. And as the stuff crystallizes, you pour it into a bottle cap, and that you'd scraped clean so that the galnia makes contact with the bottle cap. But then how do you probe it? Well, here's the problem with getting things from books. They say you use a cat's whisker. They do. It doesn't work, I can tell you that. And my cat wouldn't look me in the face for days. So I thought about this for a while, and I figured I must be misreading this. I'll bet it's jargon. And so I tried safety pen. I happened to have a safety pen around, and that brought in all the stations I could possibly want. It was just wonderful. I could get Louisiana and the kind of music I had never heard before that involved banjos and guitars and people wailing. It was wonderful. So I hung out my shingle saying I know something about radios now, and people began bringing me their table radios and their consoles and such. And in the most case, it was just a question of rattling a tube around to find the tube whose filament had broken or that had lost cathode emission, and then you plug a new tube in and your magic, it works. If only we're always that simple. At other times, the style of the day was to have a coil of wire wound around to energize the speaker that didn't have a permanent magnet in it. And that wire was very fragile. And if the radio is dropped, that wire breaks. And so you use an ohm meter to check that out and then repair the broken wire. And it was many, many radios. I saw Atwater Kents and others. I wish I had them now. They were works of beauty, things of joy. Then televisions and such. But there was still this mystery. How does it work? I had built big induction coils and I could get transmission over around 10 feet, but not further. So I filed it as one of those mysteries that might evolve, and might get answered at a later time. There was an interlude at Camp Roosevelt early in high school. Went off to the camp with 30 other juvenile delinquents, and watching, it was on break during one of the break hours, and looking out across the bay. You can't, at this camp, you can't see the further shore. It's almost as if the next thing was actually England, although in fact it's the eastern shore. And the waves began to build up a little bit, and then they began to show white caps, and then I couldn't see the white caps. The whole thing was just a sheet of fog, and the tent was flapping around like crazy. And the camp counselors came and collected us and threw us into the storm cellar, and there was this big commotion as the hurricane came over. And you can see the track of the hurricane coming up the coast, and that's Camp Roosevelt. So it sort of had a gun sight on it aimed at us. 4 hours later, we got out of the storm shelter, and my tent was the only one that was still there. It was there because there was a huge tree blown across it. So the rest of the camp was stripped. And years later, this set me up to pay a special attention to the GOES satellite. that Goddard works with. Boy, I had been there and wished they had had GOES at that time. They just couldn't make those kinds of predictions at the time of this hurricane. Another adventure I had was, I loved airplanes, so I was bicycling out around Washington and bicycled from College Park, where we were living at the time, over to Andrews Air Force Base and bicycled in and waved at the guards. They waved back. Those were simpler times. No badge. And I was looking and admiring at the various airplanes lined up on the landing strips, and off in the distance I saw a B-29. And so I bicycled up to it. Now, Tibbetts wasn't there, but it was the Enola Gay, and that's the view that I got of it. And so I thought, gosh, that plane's back in my life again. So I crawled inside, you lean my bicycle against the landing wheel, and there's a little place in the front landing area where you can go up. And I spent about an hour in the pilot's seat and the co-pilot's seat, and especially in the bombardier's position, wondering just what was going through the mind as they flew over, this plane flew over Hiroshima. So the Enola Gay once again came in. They had been moving it around the country, and it happened to be at Andrews Air Force Base for a few years. Then got to go to college. Amazing. And there was a brother Albert who took a summer course from, as a freshman going into sophomore year, on the subject of advanced algebra that I didn't even know existed as a subject. And what an electrifying experience that was, to see that beyond the arithmetic of the counting numbers, one could generalize to a number of other number systems. The counting numbers, the integers, the rationals, the reals, the complex numbers. And I began to sense, you know, maybe this goes on for a while. And I was becoming aware that physicists measure things, and they report the results of those measurements using numbers, but physicists measure different kinds of things, and it requires different kinds of number systems to report these measurements. And there are distinctions between those number systems that are integral to them and basic. It is not the case that the counting numbers are well thought of as a subset of the integers. They're different. There's a subset of the integers that behaves like them, but they belong to different systems, therefore they are different. And so what is the character of a particular kind of physical measurement that points you to using counting numbers or real numbers or rationals? And are there behaviors of general character, such as groups, rings, fields? And all of this began to become available. Later, one could see that one way to describe the birth of quantum mechanics was to replace position and momentum, instead of reporting them as real numbers, to report them as operators on a vector space. And this begins to capture the quantum mechanical interrelationship between the values of these properties. What an amazing experience. Karl Hertzfeld, another amazing experience. And now the gentleman had worked for a while with Arnold Sommerfeld. And Arnold Sommerfeld had worked for a while with Klein. This is the Klein of the Erlanger program. And the Tops, brilliant mathematician, became seriously ill, recovered, never did serious math again, but turned his attention to a problem that he was vividly aware of. So many teachers, people who did some teaching, were aware of. A student came to him and said, I love fill-in mathematical subject. And Klein had to say, give up that love. There's only 3 places in Germany at which you could earn a living doing that. And the guys in those positions are young and healthy. Fall in love with a subject being practiced by somebody who's old and decrepit. Timed so that at the moment you graduate, he's retiring, either by dying or resigning. What Klein turned his attention to was encouraging business and industry create jobs for scientists. You will like it. And they did. And the number of job openings increased dramatically. And this is one of the reasons why Germany was such a formidable foe in World War I. As a single example of it, the British were struggling to embargo the Germans from getting, blockade them from getting to the guano mines in South America, because that's where the nitrates were coming from, out of which the high explosives were being made. And so the British High Admiralty was saying, cut that supply line, the war will be over in 2 weeks, and we can all sing jolly songs. So they cut off that supply route, and the Germans began using the Fritz Harbor process, extracting nitrogen from the air. In fact, better than from guano. The chemistry that was now available, partly because the jobs had been funded as a result of Klein, and partly because of the work of John Willard Gibbs, which was taken seriously in Germany, although not here. Klein was looking around for a colleague and settled on Sommerfeld as a person who could write such articles as The Theory of the Journal Bearing, relating the character of lubrication to the effectiveness of the behavior of journal bearings. A terribly important piece of work, and many others that had industrial impact. One of my favorite examples appears in his book on optics, published at the end of World War II. The head of the German Navy, Dornberg, comes up to him and he says, the Allies are much too good at taking out our submarines. We think that they're using radar on the snorkels when we surface to recharge the batteries. I want you to make a black paint that will be radar absorbing. And Arnold says to himself, well, paints get to be absorbing by letting the radiation go into them for a half a wavelength or a quarter of a wavelength. It's not a surface effect, it's a volume effect. You got to get the radiation inside so it can be absorbed. We're talking 3 centimeter radiation here, sometimes more. How do we make a paint that thick? So he says, well, we don't have to. It has to be that thick optically. So he takes ferrite beads and he bakes them in hydrogen, gets the permeability up to around 50,000, and mixes it into a putty. And that shortens the wavelength by the square root of 50,000. So it now comes down to a fraction of a millimeter. Now you can paint it on. But it's not good enough. You need to not do it all in one layer. You have to grade it a little bit, change the density of the ferrite beads. Because if you go from unit propagation constant to a very different one, you get a reflection just from the index change. So Arnold Sommerfeld looks up the work he had done on the WKB approximation, having to do with quantum mechanical wave tunneling into a complicated barrier, and says, here is how we change the index of each of the layers, and here's how many layers we'll need for an adequate approximation. So this is in his book, Optics, of which there's 3,000 copies in the country, that managed to stay around even while we were pretending that stealth bomber paint was such a mystery or such a secret. Oh, that's Arnold Sommerfeld. Clever guy. Now, he wanted to do the same thing, and he adopted Karl Hertzberg, Hertzfeld, as his colleague on this. Karl Hertzfeld had written a paper a little while ago called The Spectrum of Water Stuff, and he said, we've got the bomber spectrum, and the spectral lines are curious in arrangement. Let's suppose that each spectral line represents a vibrational frequency of the electron in a potential field. What would be the shape of the potential field that would give us the bomber spectrum? This echoes a little bit the work of Coates, the student of Newton, who asked himself, if I've got the orbit of a planet, can I calculate the force field that that planet is in? It's the backward problem from the usual textbook. So Sommerfeld worked it out, and he got the shape of the attraction between the electron and the proton that would reproduce the bomber spectrum. And it was ridiculous. It just couldn't work. Now, you can't blame him too much. When he published that paper, he was 14 years old. And he returned to the problem as an adult. We chatted one day when he was about 70, and he said, I figured out what the difference is. I went back and looked at the work, and I made a mistake. And Niels Bohr did not make that mistake. Niels Bohr did quantize the momentum of the electron around the proton, but he also quantized the energy images. So he had a tad of QED in it, quantum electrodynamics. He did not set the frequency of emission equal to the orbital frequency. He set it to the change in the energy between orbits. So Bohr has 2 quantum mechanical events being captured in the Bohr theory. I only captured 1. So he goes back and he puts in that aspect of E equals h nu, reruns his calculation and gets the Coulomb law out of it. So it took him a while to understand where he went wrong when he was 14, but he stuck with it. And absolutely characteristic. He described to us the Bohr theory, and he then used it to understand the periodic table. And the way he showed us was to write the periodic table down and write the energy levels for each of the atoms that were important. All 92 of them, out of his head, from memory, covering the whole board. Patient, learned scholarship. He also knew lots and lots of people and would tell us the stories of their time in ways that were just charming. It made us feel we were part of the tradition of science. A wonderful experience. He had decided to work with Sommerfeld, and people said, hey, we need somebody to give a course of lectures on quantum mechanics and relativity, and you're it. That's sort of a Neil deGrasse Tyson of his time. And he was given a sum promised for the lectures, with which he could have bought and planned to buy a Duesenberg, a remarkably expensive car. Then hit the Weimar Republic collapse, and at the end of the summer, he could buy 1 postage stamp with that salary. So he turned around and he came to the Johns Hopkins University, and then they ran into the depression problem too, and he chose to come to Catholic University, where he put together a sensational physics department that I had the good fortune to encounter while it was running very smoothly. We had Talbot, who had cataracts in his eye from lining up the cyclotron beams, getting them on target. We had Malcolm Henderson, who had sat in the piano boxes with Rutherford, getting dark adapted so he could see the spinthariscope flashes of zinc sulfide as the particles came through, and more modern work as well. So, grand place. Karl Hertzfeld was just a sensational thing. They gave me a physics lab to teach when I was a junior, which pleased me on the one hand and frightened me on another. The experience taught me something I think every teacher learns rather quickly, and that is that who really learns in the course is the instructor. That's the instructor's secret weapon for becoming aware of things. And I became aware of it when I gave them a lecture, and they obviously didn't get it. And so I reworded it and worked much harder on it, and I gave it to them, and they still didn't get it. So I took my jacket off, and I taught that thing like I've never taught it before, covered the board with equations, gave examples, and you know what? I understood it. It's a wonderful experience. I recommend it. I walked across the street and worked with Emerson Myers while I was in college. He created the first electronic music studio around the area, and he tasked me with a challenge. He wanted to build a piano, and he asked me to build him an audio oscillator, which I could do for around 20 bucks. And now he wanted 88 of them, which was more expensive, but more troublesome. How do you tune the 88 oscillators as if they're a musical instrument? The parts out of which these are usually made drift, and they don't stay tuned for very long. So I worked with him on that challenge for a while. He finally decided, both of us decided we couldn't do it, so we went and got a Moog, one of the first in the area, and he's well celebrated now for being one of the pioneers of electronic music. I had this odd experience. My sister wanted to go to Catholic University in music, and so my mother, being a mother, called up Emerson Mayer and says, "You're working with my son." He says, "Yes." She says, "Well, I'm interested in sending my daughter to your music department. Is it any good?" And he said, "Well, we are accredited, our students get jobs, people seem happy there. Yes, I would say it's good." She said, "Well, she's interested in piano. Is piano any good?" And he says, well, we have all new instruments every 2 years. We keep everything in tune. The studios are acoustically isolated. We have excellent instructors and individual attention. And so she's happily reporting this to me in the evening. And I said, well, you do know he's the chairman of the music department? And especially his piano. So she says, well, I needed to know. And I guess he would. We also became aware of Feynman's approach to quantum electrodynamics. It was 10 years after the Nobel Prize. And a particular challenge that they set me to work out was Brillouin scattering in liquids. And this was a fabulous thing to work on. You take a light beam, monochromatic, and you illuminate a liquid, and the phonons in the liquid act as a refraction grating actually, and they bounce the light back. And so by looking at the angle of the scattered light, you control the frequency of the wavelength of the sound wave you're examining. And the brightness of the light gives you the intensity of it. And the frequencies are wonderfully high, 10 to the 10th, 10 to the 12th cycles. So folks were interrogating the properties of liquids using quartz crystals and other things that would get up to about 10 megahertz. And suddenly we could leapfrog over that and put points on the plots that were 10 to the 10th, 10 to the 12th. So I was set the task of researching this area and found that it had been well developed by the Indian physicists using very bright lamps with filters and exposure times that might take a week. But we had just gotten inexpensive lasers. And so the question was, would lasers make this possible? And the answer was yes. And so the whole field became reactivated quite a bit. There was a technical challenge in that the resolution was still not quite good enough. And so I delved into the issue of line shape functions and found I could increase the effective resolution of our equipment by about an order of magnitude by attending to the instrumental line width effects. And so that got reported at one of the conferences. And it's what can happen in a school that puts an undergraduate to work on something. And it's good. It's one of the best things that you guys and gals can do here is put the interns to work in exactly the same kind of group efforts and have them present things. It's a radical experience. And grade school and high school tend not to teach it. And that's a sad thing. The whole heart of the scientific communication process seems to me to revolve around people talking with each other. And the whole school system is organized around keeping the work private and separate and don't talk to each other. And there's a tension there that has hurt me a great deal. And it only began to relax a little bit at this time. So went off to the Gordon Conference on this subject to talk about it and learned another aspect of science. The fellow who was putting me onto this, Ted Lidovitz, said to a colleague who had just given him a lovely cigar, and he says, aren't you going to smoke it? And Lidovitz says, how do I know if it's any good? And the guy says, try the scientific method. And Lidovitz says, why should I give it to my graduate student to smoke? You learn a lot at Gordon conferences. Got to graduate school. We had a Japanese gentleman come in to teach mathematical physics. So we sat in the very back of the room so we could see the entire 50-foot wide blackboard display in this oddly shaped room, like a shoebox, but very wide. And I couldn't understand a word. So we copied the notes down. The notes were immaculate. And so the next class, my buddy and I split up, and I sat down in the front row so I could hear the words. And he was sitting in the back word so he'd be sure to copy everything. That's when we found out that he was speaking Japanese. And over the next year, he taught himself English and did a fine job of it. And I eventually wound up doing a PhD with him on thermodynamic two-time green functions, which was just a lovely thing to be involved in. He put us in touch with Japanese physics. He had a conversation with me once. He had worked, he was an officer in the Japanese Navy, and we had been so effective in the blockade that much of the Navy was starving, and he contracted tuberculosis, as many others did. And so he was shipped off to a city that had never been bombed for recovery. And it turned out to be Nagasaki. And so he's in the process of recovering when the entire window transfers from one side of the room to the other. Now, Tanaka had 1 degree in atomic physics and a 2nd degree in statistical mechanics, and so he entertains himself while the glass and shrapnel was being cleaned up, wondering, what kind of blast was that? It clearly was nuclear, because it was a single explosion and it was distant, and he got about 10 kilotons. He'd used much the same technique that Fermi had used when Fermi tossed a handful of confetti up and then watched how far the confetti was slammed by the shock wave. Meeting different cultures. We attached to Clyde Cowan, and such a sensation that was. It was a delight to be talking with one of the co-discoverers of the neutrino, practicing a very different style of physics than the parlor physics that Catholic University had mostly been using. Clyde thought big. When he was transferring his radiation license from the West Coast to the East Coast, he's looking down at the clerk and he's saying, "Nah, boy, you wrote M small case, millicuries. I'm licensed for megacuries." He had been the scientist in charge of the Mike explosion and really was intimate with thermonuclear events. He was interested in populating the Pacific Ocean at a depth where there was no light, but the water was clear, with photomultiplier tubes. He wanted to turn the Pacific Ocean into a neutrino detector. This was about 1962, 63. He had had the idea earlier. Now we almost have, although we don't use the Pacific Ocean. We use super pure liquids of one type or another, and many detectors, but it's still, my goodness, the idea of turning 1,000 cubic kilometers into a Cherenkov into a neutrino detector is still a haunting idea. We chatted, of course, about the impact of being able to see every nuclear submarine in the world and every nuclear pile, and he said, we'll deal with that when we have the issue. Clyde Cowan, science all around. It was a radical change from growing up where I had no one to go to ask, how do you pronounce the words? What's really the case? Is atomic theory that I hear about been confirmed or not? And such. To seeing people doing it. Went over to American University, and different times. I finished my degree, I wondered what I'd be doing, and so I called them up and I said, hi, I'm in the market, would you like a professor? And they called me back the next day and said, yeah, report on the next week. And so I started off on a tenure track at the American University. And the Mansfield Amendment hit at just about that time. When I got there, the graduate courses I was teaching in quantum mechanics and others had about 40 to 50 people in them. Then it dropped down to 2 to 5 people. You go over to the library stacks and you will see this cataclysmic impact as the thickness of volumes collapses from thick to thin. It was quite impressive. The promise had been that the National Science Foundation would get the money that the Department of Defense had been sending to universities and other scientists. And some people actually believed that, but it never really happened. The Defense Department got to spend things on that relate to destroying property and killing people, and the scientists had to look around very hard for money. I mention that because it happens from time to time. I was able to work with some graduate students, and just every one of them was sensational. I don't have time to talk too much about them. Well, one of them, the computation of the second virial coefficient of the water dimer, turns out to, oddly enough, be useful here at Goddard. And it led to some researches on how transparent is the atmosphere at certain absorption lines that are caused by the vibrations of the water dimer. I was not knowing about that at the time. What I did know was that Poppel had just published electronic computation on the potential energy between two water molecules for 1,000 different configurations of them. And I thought I could probably use that to bootstrap a computation of the second virial coefficient. And what I was really interested in was the third virial coefficient. But we never got to that. It turned out the second virial coefficient was enough. We had to augment his calculation with some other effects, but we got agreement between the measured second virial coefficient and the calculated one to within about 20%, even though it changes by several orders of magnitude, using Planck's constant and the mass of the electron, elementary constants. So it was computation of a thermodynamic property from first principles, and made me very happy. Charles Brown also did wonderful stuff. Kenneth Oscar, I must mention, his daytime job was killing people. He worked for special forces. He didn't do it personally. He just arranged for the weapon systems. And he hated it, but thought there were reasons that it should be done. He became aware that Navy guys were playing tricks on each other. They would take a microphone and use it to amplitude modulate the intensity of pulse radars. And there'd be a guy on the end of the carrier, nobody around him for 100 feet, and they're saying, "Hi, George, I think you just missed a cigarette there." And he'd hear it in his head. And, well, there were two questions. We wanted to know why, but also we wanted to know, is it dangerous? So I set up a committee that involved biologists, microwave experts, some other folks, and we asked 850 rats at Walter Reed to give their all in the interest of science, which they did, and we established that, either that or lawyers, and we established that this radiation pulse breaks down the blood-brain barrier, designed to keep the heavy molecular weight serums in the blood out of the brain tissue. This happens with prize fighters and other people who have repetitive head shocks. It is very bad. If you think that thinking is good, you stop thinking after a while very easily with this. So it is bad. And we were able to rewrite the microwave damage specifications for the country. So this kind of damage doesn't happen. The older specifications are written in terms of the rise of the brain tissue. And you don't get much rise, a tenth of a degree, out of this pulse. But the sharpness of the leading edge of the pulse is terribly destructive. So that. Now, I read in the Washingtonian magazine that there are people who believe that the government is talking into their heads with some sort of magic machinery, and they have actually done some homework on this, and I was reading that they had managed to trace it to some work done at the Walter Reed Hospital at the time of this dissertation. So there's a way in which Kenneth Oscar and myself and the others are responsible for the tin hat syndromes that you sometimes hear about. Amusingly, well, I don't know if any of this is that amusing, but if you do put the tin hat on, you increase the resonance of the cavity, and the damage goes up by a factor of 5. So if you're going to do a tin hat, make sure it's a complete hat and no holes in it. And Don Day did brilliant scattering, a follow-on of my own, and was able to confirm a theory I had earlier, which was very pleasant indeed. Don Day is an extraordinary gentleman who has devoted his life to being an excellent teacher and inspiring students far and wide. And I have met several of his students at Goddard, so it's a case of seeing grand students right now. Lady comes down and tells me she wants to be an astronomer. And I told her, hey, I can't be an astronomer, a guide of dissertation in astronomy. I don't have those credentials. But I know somebody who does. And I walked her down to Vera Rubin, and I said, Vera, you're doing this amusing and amazing work in dark energy. This was in 1968, 69. And perhaps you'd like a student. And so Vera was absolutely courteous and charming. The student turned out to prefer high energy physics in the end, but she had a chance to get in on the ground floor of something quite amazing. And more stuff here. It would be fun. We're pretty much out of time. I'd like to talk about Howard Reiss and how in order to explore his theory of taming the nuclear reactions of thorium and making them controllable and easy, we filled a child's swimming pool with ice water and took a huge copper coil and drove it with 660 volts line voltage to really get the largest tea boiler I had ever seen. There it was boiling away, trying to give us an intense low-frequency field that could cooperate to produce a bazillion photons simultaneously driving a transition, something that followed beautifully from his theory. Well, before we had a chance to complete the experiment, 3 of the largest guys I had seen in a long time, armed with mighty weapons, came in and said, "Ah, it is you. I thought it would be somebody at the freak university." And they turned out to be from the Navy Deep Submarine Communication Group that's about a mile up the road from us. And we were shutting down the entire submarine communication network. So we told them, oops, and turned off the equipment. I have worked with GOES failures driven by lamps. The GOES looks like this. It's a spinner. The GOES series is a spinner. The telescope staring straight up the middle into a mirror that is deflected to look at the Earth. So each time it spins, you get a scan line across the Earth. And because it's heavy and free of influences, it spins at a remarkably uniform rate. So your scan line, the point at which the telescope is aimed, is known with amazing precision. All you now have to do is know what the tilt of the mirror is. And this was handled by a company, BEI. Baldwin Electronic Instruments in the olden days, renamed as BEI. They made encoders for shaft angles. And the encoder used the light bulb. And the light bulb was burning out. And the reason the light bulb was burning out was mysterious to start with. In fact, Santa Barbara told Goddard that Goddard was a bunch of idiots because they knew that those bulbs were good for 17 years minimum. So it couldn't be the light bulb. And we said, give us some examples and we'll find out. And it turns out it was the light bulbs. They were burning out in as little as 9 months. And the mission was supposed to be 3-year target, 5-year hope. And so it was not good at all. And when the encoder burns out, that mirror can no longer be tracked. And that means both the imager and the sounder go blind. There's other things that GOES does, but imaging and sounder is awfully important. And so what was causing the discrepancy? And 2 things. The Santa Barbara Research Corporation had done an accelerated experiment, because who has time to run the experiment for 3 years? So they turned the voltages up and burned the light bulbs out in times ranging from 3 minutes to 3 months. Plotted it on log paper, God bless log paper, and got a straight line and said, we're done. There's a second killer mechanism that enters at 6 months, just beyond their data, and it's flat. So the ultimate lifetime burned in this way is a year or so. But the brother-in-law said, how hard can it be to make a lamp? And so he was turning out these filaments himself, and he was doing a very bad job of it. And the acceptance criteria had been put so low that it wasn't detected with these new lamps. But I guess you could say we were using the GOES satellite as a detector for when the lamp was bad. It's a very expensive way to do that kind of thing. And it taught me the usefulness of making site visits and not depending on the paperwork that says, we will notify you if there's any process change. Trust us. I only learned recently that when Ronald Reagan voiced to Khrushchev, trust but verify, he was being more subtle than I knew. It's an old Russian proverb. He was feeding it back to Khrushchev. But it's a good proverb for a person in this line of work. Trust but verify. Now, gosh, I got so interested in telling you how I got here that I haven't had too much time left to tell you what I've done here. Gosh, I'll be extremely quick. Fiber optics, we put a bunch of it into the International Space Station, where we were trying to, and as Boeing was making these up, they found that the insertion loss of the fiber optic was falling below the specified value. So what do? Ha! You change the acceptance spec. So, and we said, okay. And so it turned out that the insertion losses got even worse. And so Boeing says, hey, let's change it again. And we said, yeah, sure. And then when this happened the 3rd time, and some of the fiber optic cables were going dark, no light through them at all, we said, time to pause and find out why. And it was amazing. When you cross-section the fiber, this one was cross-sectioned by breaking it, you see these defects in the side of the fiber, and they're mysterious. There's a pinhole, a shell of the coating, the plastic coating, around the glass of material. That hole is allowing a hydrofluoric acid to get through. And the hydrofluoric acid is etching the silicon layer rather slowly, so it etches it as a sphere. But when it gets to the inner part of the core of the fiber optic, which is germanium doped, it says, wow, and the corrosion. So we would call these rocket engine defects. And eventually we understood them, except what's causing the pinholes? And also, where does hydrofluoric acid come from? Those worked out too. The hydrofluoric acid comes from the FEP polymer that's surrounding the fiber. And DuPont, who sells the little pellets, says, get them dry, bake them out at 150 centigrade for an hour, and then store them under dry nitrogen and put them into the extruder and squeeze them out into the tube at no hotter than 404 degrees centigrade. Now the company doing it, BIC, B-I-C, said, who's got time for that? So they would take the pellets off the truck and throw them in the extruder hopper. And if you turn the temperature up, it extrudes faster. So they went up very high. And this decomposes the FEP into a into ultimately hydrogen fluoride. So now we knew where the hydrogen fluoride was coming from, and we looked for it, and we found it when we went looking for it. But then the holes. Now, in the Old West, when the telegraph wires went up, but the cowboys were still riding along, and it was a windy day, you would hear the telephone lines singing in the wind. It's aeolian vibrations. Von Karman eddies form around the fiber as the winds go over them. Well, these fibers being drawn down from the draw tower are being shot at. There's a jet of gas blowing on them with the carbon coating on them, and it does. But it also gives them, excites aeolian vibrations. And so I looked at the tension of the fiber, and I got some masses. And I found out that the vibration frequency that they were exciting, exactly together with the draw speed, exactly matched the distance between these holes. And so, done. And it also explains why some F-22s and other military aircraft who use the same fiber are having them break. Now, we think we fixed this. We hope we fixed this. Boeing used better stuff to go into the lab that used this fiber optic. There's about 2 or 3 kilometers of it on station right now. So periodically I call up and I say, hey, how much of it is working? And I get the answer, it's all working. And I say, how do you know? And they say, well, nobody's complained. And I say, how much of it's been turned on? And they ruffle, ruffle, shuffle, shuffle, none of it. So the station could be doing a little more science than it's doing. And I'd like to have the effectiveness of our Get Better techniques checked out. Exactly the same damage mechanism attacked Triana. We used plugs with long wires pre-attached to them, shipped to us in plastic bags. And one of the technicians, clever guy, takes the connector out of the plastic bag, and the nickel-coated back shell is black. And he says, that can't be right. And he's looking at the silver coating on the ends that are exposed. That's black too. So he brings it over to Terry King, and Terry King is staring at the golden pins, and they're coated with green crud, which is copper fluoride. And he pokes at them, and the whole pin collapses. The entire copper under support has been converted into hydrogen fluoride. It's again, the FEP insulation, the fluoropolymer insulation, has been put on too aggressively, per DuPont's rules, is exuding hydrogen fluoride, and it's trapped by the bag. We believe that some mirrors have been damaged by the massive amount of wiring present in some of the boxes, and it attacks all kinds of mirror coatings and frosts up the windows as well. We saw the same hydrogen fluoride attack on Landsat data recovery mission, where we said, hey, this is a problem. And they said, hey, it's not a problem. And they quoted us some specifications that say, if when it appears on their shipping dock, there's no obvious damage, then it's not a problem. We don't care what it looks like when we put it into the spacecraft. So this business of what the specifications are is worth taking very seriously. And there we are. We're home again.
Wow. So let's give him a round of applause. I think we'll take 3 comments and then he'll be around here to answer anything else. So any quick comments or questions?
Yes, Harlan.
As I recall, you worked on the investigation of the Toyota runaway acceleration.
Oh, did we ever? Yes. Ludmilla, stand up for a second. Ludmilla is the one who actually saw the tin whisker in the Toyota pedal. The Hall's, yes. And one of Don Day's students, I might add. So yes, the Toyota investigation at Goddard proceeded differently than is loudly advertised in the public press. The public press says there is no electronic problem found in the Toyota acceleration system. That's simply a lie. There is a character of unintended acceleration that we have seen rigorously established for 2 pedals, each of which was sent to me from a failed car. And it's caused by tin whiskers. Toyota went from saying tin whiskers are inconceivable to saying they are unlikely to saying, well, yeah, there's a couple of them, to saying, well, everybody has them. But they don't cause any problem. It's wrong. They do cause problems, and I think they've killed some people.
What's a tin whisker?
Metals sometimes do crystal growth. Now, I mentioned John Willard Gibbs. John Willard Gibbs taught us an immaculate story on what phases are thermodynamically stable. That was more than a century ago. It would be nice, century and a half, it would be nice if we knew which phases grow quickly and which phases grow slowly. We don't. That still remains quite a mystery. But we do know that metals tend to form grains of different sizes, and there's a curious thing that happens predominantly with tin, zinc, and cadmium. One of those grains out of 10,000 or 100,000 begins to condense tin or zinc or cadmium on its root, and it jacks it up. And this continues to happen, and so you have a grain that is now long but remains the width of a grain. And the length can be up to an inch. It probably can be longer. We just haven't seen them longer than an inch. We have seen an inch. It's commonplace to see them at a 1/4 inch or smaller. Why it does it to that one grain in 100,000 remains mysterious. We understand some of the dynamics of it, and I can chat with anybody who wants to hear more about it. But there's an essential part of the dynamics we do not understand, and that is why that one grain out of so many accretes, and none of the others do. It's so much like the Harris cartoon of the very busy blackboard symbols all collapsing down to the neck of an hourglass and then expanding out again. And the guy is saying, right here, a miracle occurs. So we don't understand the miracle yet. We understand both sides of it. And we understand the dangers of them. They were in the Shuttle where they caused the failure of one of the boards. They are in guided missiles. The cruise, we have Hellfire missile was a 10% return rate steadily because of malfunction caused by tin whiskers. There's been pacemakers that have collapsed under tin whiskers. Nuclear power plants have been shut down by the alarming equipment going off because of a tin whisker. That can shut the plant down for a day to a month. Also, computer centers are attacked by the zinc whiskers coming from the ductwork and under the floor tiles. And the state of Colorado had to close its statewide computer center because of zinc whisker infestation. And we believe, I went looking here, and one of the rooms not far from where I work was shut down because computers would not work in it. And so people didn't try to solve it, they solved it by moving to a different location. So
I think, okay. Yeah, so I think he will be here for a few more minutes if you want to talk to him.
Okay.
Because I know there are some people who are going for meetings, so I want to close it there. So once again, let's thank him one more time.
okay. Thank you.